Good morning. My name is Caroline Bernier. I'm an RFIC designer at CLT in Grenoble. And I've been designing ultra-low power wireless transceivers now for about 10 years. So the topic, my talk is entitled Channel-Aware Strategies for Ultra-Low Power IoT Wireless Links. So the context of my talk is, of course, wireless sensor networks, which is one of the fundamental pillars of the Internet of Things. And the focus of my talk today will be on the low power specification that is required for these systems. And specifically, I want to put a specific impact on the notion of deploy and forget. What is deploy and forget? Well, it's the idea that once a communicating node is in our home network or is in the IoT, the idea is that the network connectivity must remain functional for the duration of the deployed object's lifetime. So whatever object that I have that has a wireless connectivity, well, it must remain functional for the duration of the object's useful lifetime. So this is, we're generally talking about years. Ideally, we're trying to focus around 20 years. If we aim for 20 years, maybe we'll get 10 years, for example. So the question here is, how can we reach these types of lifetimes for self-powered wireless applications? So, of course, you're probably going to power the node using a combination of batteries or harvesting, and you're, of course, going to use energy and context-aware power management as Edith presented, but this is not the focus of my talk today. My talk is more about smart context and energy-aware protocol layers within the communication stacks. And of course, these smart protocols will be required in order to reach these types of lifetimes at all levels of the protocol stack. But today, the focus of my presentation is on the low levels in the physical layer specifically, and more specifically on the wireless channel. So why are we going to talk about the wireless channel? Well, we observed that for low complexity wireless sensor network applications, is the radio transceiver that's often the most power hungry element in the node. And today's transceivers, how are they designed? Well, they're designed to face worst case propagation. And therefore, during the node's lifetime, there are moments when then the design margins will lead to significant waste of energy. For example, when wireless transmissions occur, there are times when indeed the signal is very weak and there are lots of strong interferers. And in those moments, indeed, the transceiver must behave in its high performance mode. But there will be times when the signal will be strong. There will be times when the interference may not be present or will be weak. So in those conditions, the transceiver is wasting power. So the idea behind all these strategies that I'm going to present is let's try to see if it's possible to save energy by adapting the performance of the RF transceiver to the instantaneous channel conditions. So let's look at what is an RF channel. So there's, of course, many components of the RF channel modeling. Of course, path loss is the one that comes to mind first. It's depending on an exponent of distance, the exponent generally being above 2, 3 being a value that's often used for indoor modeling, for example. But path loss doesn't take into account the shadowing components, which are due to large-scale obstacles in the propagation path, and which means that for a given distance, the signal-to-noise ratio will be very different from one transceiver to another. So shadowing is often modeled on a log scale using a normal distribution, and if we review the literature, we see we have standard deviations in the order of 6 dB, which is the average number for channel measurements. But path loss and shadowing are not the only two effects affecting narrowband communications. Whenever there's mobility in the environment, either of the node or of people walking around, mobility will induce multipath fading, which is due to positive and negative reconstruction of the electromagnetic wave. And we can model this fading using the notion of Doppler spread, which is proportional, and the Doppler frequency, FD, which is proportional to the speed at which the elements in the environment are moving. For example, for a wave at 2.4 gigahertz and a moving speed of 4 kilometers per second, this leads to a coherence time of the channel of 45 milliseconds. So in the measurements shown below, what we see is that there's a receiver that is fixed and a receiver that is moving away at a walking speed from the receiver. And what we're seeing is that the average path loss is indeed increasing as we see the level of the signal is going down. But we also see the effect of multipath fading. We're seeing 30 dB dips on the signal. And if we zoom in on a little part of this figure and we look at what is that little green triangle there, that little green triangle is the maximum length of a zigbee packet. So we understand intuitively that that multipath fading is going to be very difficult to combat because from one transmission to another, the channel characteristics may have changed. So this type of fading is called slow because the packet is smaller than the coherence time of the channel. And it's actually the most challenging type of channel for which to design a communication system. Fast fading can be combated using equalization, coding, etc. This is what is done in all cellular communications. But in low complexity, low power systems where you can't afford these high power algorithms, slow fading is a real challenge. So the idea I want to get across is during its lifetime, the 20-year lifetime that the wireless node is going to be deployed in, for example, in your home area network, it's going to see very probably considerable variations in RF channel. For example, if the nodes are mobile, if it's your child's teddy bear or whatever, well, as it moves around the house, it's going to observe variations in path loss and shadowing in time frames that may go from seconds, minutes, hours, days, etc. As the node moves within the space covered by the wireless sensor network. And even if the nodes are placed in static locations, for example, we have a wireless thermometer placed on a window somewhere, well, the user requirements may want and lead us to choose to displace the node as your needs evolve. And multipath fading, well, that is going to affect the channel whenever either the nodes are mobile or people are moving around. So here at the bottom, I've just illustrated what the coherence time of a channel could be in a typical office building where people at night are not working and they arrive at 9 in the morning and then at noon while they go for lunch. The coherence time may go from hours to milliseconds. And this is something that might potentially be harnessed because that means that the specifications for multipath fading, for example, will change during the day. So what kind of dynamic range are we looking at? So I plotted the three different channel effects, path loss, shadowing, and fading, and we're looking at the dynamic range that represents for the signal. If we trace path loss, for example, up to a distance of 100 meters, we're looking at 60 dB. 60 dB is huge, it's 1 million, so that's a huge factor of signal changes. Shadowing, well, if we plot a normal distribution with a standard deviation of 6 dB, well, we see we have potentially about 30 to 40 dB dynamic range. Again, huge dynamic range. If we look again at the measurements of fading, multipath fading, again, we see the 30 dB dips are really frequent, so we're facing a lot of dynamic range. Unfortunately, channel is not the only effect that's going to have an impact on the communication quality, the link quality, because during its lifetime, the node will also probably see considerable variations in RF interference. I'm at home, my Wi-Fi is on, I'm downloading a film, suddenly the channel is very busy, or my neighbors are but at night I'm not using it, so that means that this interference will vary in time due to user usage patterns and as new RF networks are deployed. So this means that in theory, the selectivity requirements of the transceiver vary in it costs energy to filter the signal, to isolate it from transceivers. Maybe we can harness this idea. So today, transceivers, well, they're built in order to provide a certain level of performance for a certain amount of power cost or energy cost per useful bit. And here we measure performance. Performance for a transceiver can be measured using many different metrics: sensitivity, selectivity, linearity, output power, well, spurious emissions. Well, there's a lot of things we can put into the word performance. But why not imagine that tomorrow's transceivers are designed like this? We can have a transceiver that is able to scale its performance and while reducing energy. And as we saw, in terms of performance, if we're just looking at selectivity, sensitivity, for example, we have potentially 60 dB dynamic range. That is huge. So what kind of dynamic range can we get on the energy for the transceiver? I'm not saying we're going to get 60 dB dynamic range, but if we could get a dynamic range of 10 dB, that would be just great. However, in order to use this idea in a real-world system, we have to be able to measure what the channel quality is, and we have to do it very finely, potentially from packet to packet. And this measuring link quality is a complicated task. Measurements show that as a function of distance, the packet reception ratios can vary from very high to very low, and it's very difficult to predict. And indeed, channel quality is affected by, as I said, channel effects, interference effect, but also hardware non-idealities. So this is a complicated task. And historically, link quality estimators, well, they use what's available on today's hardware. They're using RSSI, LQI, SNR, or they're building software type metrics where they're counting packet rejection ratio, or acknowledgement, number of retransmissions, number of acknowledgements required, etc. They're measuring all of this types of data in order to build an image of channel quality. But what the research is showing is that all of these LQEs have limited precision and in actual usefulness. What I predict is that tomorrow, measuring link quality will become something very smart and very fine-grained. For example, Jamieson and Balacrian, they presented in 2007 a very interesting idea, a very powerful idea called soft phi. And the idea is that for each data bit that we receive or a received signal, we can also construct some information that gives us information concerning the probability that the signal is correct or that the symbol is correct. And thanks to this information, we can do lots of neat and fine things in order to understand what is the type of channel that the signal traversed, in order to see, what am I facing? Am I facing shadowing? Am I facing fading? Am I facing interference? Am I facing a collision? Et cetera, et cetera. So I'm pretty sure that it's actually pretty simple to propose many new types of link quality estimators, but unfortunately they're not available on hardware today. But I predict that we'll have to make them available on tomorrow's transceivers, and that's what's interesting for me, is like, what is the specification of a transceiver for tomorrow? And another interesting point is that since we're going into finer and finer microelectronic nodes, we're going to have more and more DSP functionality, so we're going to be able to construct finer and finer, for example, FFT-based analyzers, or we can imagine all sorts of things in order to analyze what's going on the channel. Of course, the implementation cost, the power cost associated to measuring link quality must be practically negligible. So we've classified in our work different LQE estimators as a function of the stack protocol layer, and we predict that there will be some component of the system, very important, a link quality processor, which will be used to identify and classify the factors that are influencing instantaneously the channel quality and provide a time-dependent characterization of the quality. So the idea, of course, its job is to select the optimal strategy at any given time, and ideally it will be able to learn about the channel and will be able to predict future performance. So we have a sense and react type of approach in which the system is able to sense information about the channel, analyze it, and decide on what is the best strategy. And now we need to be able to act onto the to the transceiver itself. So imagine you have some type of link quality saying I'm having this type of channel. How can you minimize the energy of a transmission cost? Well, since energy is simply the integration of power over time, you have two options. Either you minimize power, either you minimize the time of the transmission. So I'm going to have an overview of these two options. And let's just look what a budget link for an RF communication is. I have a transmitter that is sending a signal at a given power PE. It's suffering channel losses L, and it's being received by a receiver at a given reception power PRX. And if PRX is higher than the sensitivity of the receiver, then we consider that the link exists. So the first idea in order to reduce the power cost of a transmission is to minimize the transmission power, because a lot of people have exploited the fact that when we minimize the energy of the biasing points of the PA, it reduces its power, its output power, and thus it minimizes its current consumption, its power consumption. So this technique is called transmission power control. It of course requires that the receiver sends back an acknowledgement information, giving it the transmitter information about the channel quality. So there's a feedback path that is necessary. And we'll see that this feedback path can sometimes be problematic. So this technique is very well known. It's used in many, many different systems. Many papers have presented many different protocols and ideas for exploiting this. They've shown that it has an impact on congestion, throughput, et cetera, et cetera. But the question that's interesting for me is, what is the impact on network lifetime? And if we survey all the experimental results that have tried to use this technique in wireless sensor network, well, they mostly come up about to 10 to 30% improvement. And 10 to 30% improvement is just, no, it's not sufficient. I'm looking for a factor of 10 improvement in energy consumption. So this is very limited usefulness. Why is this limited today? Well, the transceivers don't have, the emitters don't have they only have a factor of 2 dynamic range on the energy. So it's not going to be, we can already predict that it's not going to be interesting. So this has been work done on the transmitter side. What about the receiver? Now there's people who, because on the receiver side, we can do the same thing. We can, when the channel losses are less than expected, well, we can change the noise floor of the receiver and therefore save power, because of course minimizing noise floor costs a lot of energy. So a lot of people have started working on this idea. For example, Doe in 2010, they presented a transceiver with a variable transconductance LNA, and they're able to trade noise figure by 8 dB, while by dividing the current consumption by a factor of 4 or 5. And other people have worked on other blocks, either on the digital sides, on the filtering sides, etc. So this idea is something that's starting to gain interest in the research community. And the idea here, if we take our budget link equation again, rather than modifying the transmission power, we're going to modify the noise figure of the receiver. And this is how we build a power scalable receiver. It has some advantages. For example, it doesn't need to have an LQE feedback path back to the transmitter. So therefore, that means it supports multicast and broadcast traffics. And therefore, it can be used independently of any MAC and network level protocol. So you can have a channel-aware receiver without the higher level protocols knowing anything about it. So that's pretty neat. And it can be very reactive. That means for every frame, it can adapt the power consumption as it goes. However, it's pretty hard to design. Well, it means it needs a lot of work, because that means we have to make analog and RF blocks that have variable bias points, and we have to be able to test them. And so the question is, before going into all of this work, I want to make sure to prove that it's going to be useful. And so, and also this question, how am I going to use it in real life? I have this multi-point transceiver, but how am I going to use it? So with my students, we started thinking, okay, imagine I have this transceiver, how am I going to use it in a real deployment? Well, there are many ways to use it. For example, you can reconfigure in a static style. For example, if a channel improves in time, you can decide to switch to a lower performance mode, but the entire packet transmission is received at a given performance mode. This is a little bit problematic because if you increase your noise figure, suddenly your sensitivity decreases, so that means their connectivity might evolve at the network level, but it's pretty easy to design, so it has some advantages. However, you could also imagine you're doing some type of dynamic reconfiguration. During packet reception, you may continuously be adapting the configuration of the transceiver, or something that could be probably easier and smarter, you could do it only once. For example, after just you do an LQE measurement, for example, a signal strength measurement on the packet preamble, and then you switch performance mode as a function of the result. So this seems much more feasible, and it's pretty interesting. And and one thing I want to observe is that static reconfiguration is pretty neat and pretty optimal in static type of channels. For example, where you only have shadowing and path loss. But dynamic reconfiguration is really well adapted to slow fading channels, which are the really hard channels we wanted to find a solution for. So the question I want to ask is, are these receivers useful? Because they need a lot of work to do, so I want to be sure that I'm going to gain energy if I do all the work of designing one. So here we made a model where we imagine that we have a power scalable receiver that's able to scale its noise figure by a factor of 10. And we did the following probabilistic analysis. Imagine we have a wireless sensor network deployed with a node density lambda. And we have a power scalable receiver with 3 modes. We fix all the other, the transmission power, the channel model elements. And what we did is we found the probability of the distance between the distance between one node and its neighbor. So this analysis is not too difficult to do. It's based on the idea of Poisson process. And so we find the probability distribution of Rn, of the distance from node D to its nearest neighbor. And thanks to this probability, and since we know all the equations for path loss and all that, including shadowing, we can draw the density probability of the received signal strength as a function of lambda, which is the node density. So a lambda of 0.01 means one node in a surface of 100 square meters. So one node per 100 square meters, it's one node, for example, in this room. So this is a reasonable density for a wireless sensor network. And so when we draw these curves, and we define thresholds which allow us to pass from high performance mode to medium performance mode to low performance mode, and we, of course, include some reconfiguration margins, it's very simple just to simply integrate the area under these curves in order to find the probability that the nodes will be in one mode versus another mode. So if we plot the results and we check different channels, an AWGN channel or a shadowing channel, and we plot the ratio, the usage ratio of the different modes, we see that, of course, as the node density decreases, the nodes are further apart, the nodes will have to use the high performance mode. But if we're looking at reasonable densities in the 0.01 to 1.001, which is one node per 1,000 square meter, well, we're looking at usage rates of the low performance mode, which are relatively high. And if we add slow fading, using either Rayleigh or Ricean models to model slow fading, well, we have results that are practically the same. So we conclude, oh, this might be useful, might be worth spending all that time to build these transceivers. Now I want to talk about the second reconfiguration strategy in order to minimize energy, and that is to minimize the time of a transmission. So here, if we take our budget link equation, we're neither changing transmission power, nor are we changing noise figure, we're changing bandwidth. And as we increase bandwidth, that means we're increasing the noise floor, and we're therefore mechanically reducing the sensitivity of the receiver. But the idea is, since we have a higher bandwidth, we can transmit at higher rate, and if we're transmitting at higher rate the same amount of data, that means our packets are shorter. And these types of algorithms, they've been used extensively in the context of wireless LAN, for example. But here, the objective in those works and those protocols is to maximize throughput. The objective was never to minimize energy consumption. And here, this is the idea. And one interesting point about transmission rate adaptation is that it simultaneously minimizes the energy consumption of the transmitter and the receiver, and that's great. Whereas the other two techniques I presented before, PSR and TPC, they minimize either the receiver or the transmitter. And they're pretty easy to design because, for example, in spread spectrum communications, all you have to do is change spreading code in order to change data rate. And for example, this is exactly what Atmel did on the recent chip, the 233. And they took their Zigbee chip, a classic Zigbee chip, 250 kilobits per second, and they allowed the user to change the spreading code, and that allows the user to trade 13 dB loss in sensitivity. Their sensitivity is going from -101 to -88. So of course, we're losing sensitivity, but potentially we can gain a factor of 6 in energy because the frames are much shorter. But of course, this depends on the frame length, but for maximum frame length, we can potentially gain a factor of 6 in energy. A factor of 6 is pretty good. I think we can do something with a factor of 6. So to conclude, here in this table is just a recap of what I said earlier, and with a comparison of the different adaptation strategies and today's energy savings that are available with the techniques that we know today. Of course, this is just initial research. So there's a lot of work that should be done on this. And I'm pretty sure that for all 3 types of reconfiguration, we can obtain factors of 20 to 30 pretty easily. I don't see any reason why we shouldn't be able to gain factors of that order. And so we could potentially have high dynamic ranges on the energy savings that are available. Just to state again, transmission rate adaptation algorithms, I honestly believe that this is a must. It's easy to do, it's easy to use, it minimizes the energy of both the transmitter and the receiver, so I'm pretty sure that this is a technique that must absolutely be exploited in the future. However, power scalable receivers, well, they're pretty neat because they have some unique advantages. They can face up to slow fading channels, and they can be used in any types of communications. So, of course, when we use these types of transceivers, we have to think, maybe we'll have to look at what's going on at the MAC and network level, because maybe the usage of the transceiver will have an impact on the higher level protocols. So, to conclude, some research perspectives. I honestly believe that channel-aware transceivers may deliver in the future ultra-low power capability for tomorrow's deploy and forget IoT nodes. Of course, in order to design these transceivers, we have to find very simple strategies to trade performance for energy at the RF design, in the digital design level, and with large dynamic ranges in order to be able to exploit the dynamic range observed on the channel. And we, of course, need to include DSP capabilities to improve fine-grained channel quality estimation at the physical layer. And of course, we have to develop intelligent link quality processors. Are we going towards machine learning? I don't know, but this has to be this is a very, very important point. And of course, we have to work with higher level protocol designers. Physical layer people cannot stay in their labs by themselves. We have to work with higher level protocol designers, because sometimes the MAC protocol designers will not want to change their protocols, and so therefore the physical layer people will have to define their channel aware transceivers and have none of this information go higher to the higher levels. But there are times when channel state information may be used by the higher level protocols, for example, for routing or for MAC signaling. And so there are times when this information you will want to have to go up to the higher levels. So I'm pretty sure that in the future we'll have to work more together between the physical layer people and the higher level people. And if you have a project and are interested on this subject, please have a chat with me afterwards.